Hi, welcome back to Kiersti's virtual classroom. Today we are talking about surface water. Why is water important? So everybody needs water, right? So water is essential for all life on Earth. If we didn't have water, we wouldn't have anything that we see on Earth. We wouldn't see any of the life in plants, animals, humans. None of that would be sustained without water. It is our most valuable resource. Okay, it's more valuable than petroleum. It's more valuable than gold. If we didn't have the water, we wouldn't be here. And 60% of your body, if you didn't know, is made up of water. And you can survive weeks without food, but you can only survive a few days without any water. Okay, just keep that in mind when you're in survival mode. All right, water is everywhere. So 70% of Earth's surface is covered in water. Only 30% of Earth's surface is land. So to think about how much water we have, but we talk about a drought a lot, why do you think that is? So one of the biggest reasons that we talk about a drought and we talk about not having enough water is because most of the water on Earth is not drinkable. So 97% of the Earth's water is in the ocean. 97%, with 3% to maybe work with. But oh wait, 2% of that is locked up in glaciers and polar ice. So we can't even use that 2%. So the 1% is what we can actually access. So that's in the groundwater, lakes, and rivers. And there's a very small fraction in the atmosphere as vapor. But most of what we drink is from groundwater. And then some of what we drink is from lakes and rivers. So most of the Earth's water, although there is a lot of it, is salt water. And salt water is not something that we can drink right now. There is some development in terms of desalination projects, and I will talk about those at the end of this lecture. But for now, let's focus on the groundwater and lakes and rivers. So that 1% is what we use for everything. We use that for drinking water, agriculture. We use it in transportation, steam power, and a lot of other things. Okay, so if it weren't for that 1%, we wouldn't be here. If we had more, there would probably be more things on Earth. So we're able to sustain the life that we have with that 1%, which is pretty amazing if you think about it. So who uses the most water? That would be agriculture. You're probably pretty familiar with that, being from the Central Valley. Agriculture uses the most water of any other industry. That includes domestic use and things like petroleum driven industries. So petroleum driven industries would be the highest in petroleum consumption, but the lowest in water, whereas agriculture would be the opposite, right? Water is the highest in agriculture, but agriculture would be the lowest in petroleum. So who uses the most water? This is just another spreadsheet. So 60% is agriculture, 25% domestic, and 15% industry. How do you use your water? Well, this depends on you and how you run your household. But amazingly enough, the vast majority goes to going to the restroom, baths, and showers. So your bathing habits and how often you use the restroom, or whether maybe you do the trick in your house where if it's yellow, let it mellow, if it's brown, flush it down, to try to save on water usage. But depending on how you run your household, you will see a different organization of this chart. Laundry takes up a huge percentage. So if you didn't know, even if you do a small load of laundry, the bin, unless you have a smart washer, will completely fill up with water before it starts doing the cycle. So that's using a lot of water, and then all of that gets dumped down basically the drain and out into the wastewater treatment facilities. Drinking and cooking is about 10%, and then cleaning about 5%. So depending on your length of your showers, how often you take baths, whether you flush every time, or how often you do laundry, you can decrease your water usage. But in Fresno so far, they haven't limited us yet. They just keep charging us more money. Yay. But you are very lucky that you can run over to your tap and turn on clean drinking water. So water that is potable means that it's drinkable. So there's nothing in it that would harm you. I know that a lot of people complain about Fresno water or some other water in the Central Valley being very, very chlorinated, but that's for a reason. It's to try to kill some of the other bacteria that can live in the water. And while some people don't necessarily like that taste, it's better than drinking some of the other things that might be found in Fresno groundwater. I used to work in Fresno groundwater industry in town, and we did a lot of treatment. So we'll talk a little bit about that in this lecture. And you are very lucky that you can turn the tap on and just drink it. They spend a lot of money treating Fresno water. So take that with a grain of salt. Some people have to spend their entire day or most of their week going to get water just to drink. So feel lucky you don't have to worry about any of that. We have issues with drought, so consumption is drying up our freshwater systems and is now depleting our groundwater. So in recent years, California has developed something called SGMA, which is Sustainable Groundwater Act. The goal is to make sure that the groundwater levels do not deplete and go down any further. They're already very deep in Fresno. The average is about 100 to 150 feet below the ground surface is where water is. And that has depleted significantly over the years, and we'll kind of play with that with groundwater in the lab. Okay. So here's an example of surface water drying up. This is in Kazakhstan and Uzbekistan. This is the Aral Sea. This was from 1977 to 2009. I think this one is 2010. So we have significantly depleted this inland sea, which was a freshwater system that was potable water, and it is now completely depleted, and it's as you can see, especially in the 2009 photograph, it is high in salt content now, which means that it is not drinkable. It has formed evaporites, if you remember from sedimentary rocks, which is high in salt content, and now it is undrinkable. So that is unfortunate. Okay, so the water cycle is really important when we start talking about water. Water does cycle through these different stages, and the ones that you're probably familiar with are evaporation, condensation, precipitation, right? So you're familiar with the evaporation of the oceans or surface water, and then the condensation of them into clouds, and then the precipitation as rain, sleet, snow, etc. If the precipitation is not quickly infiltrated into the ground and makes it into groundwater storage, which is where water is stored in the pore spaces between grains and between rocks, it will run off. So it either is snow that is melted and is snow melt runoff, or it can be surface water runoff, and we'll talk about some of those in a second. Okay, so water is in a cycle. The issue that we see today is that we have so many people absorbing or intaking that water, it's getting stuck in the human stage and in our waste stage. So as soon as we can transform wastewater back into potable water, we're going to be set, and we're going to be back on this cycle, and we're going to be part of the cycle. And this will kind of change. We'll have some little wastewater treatment facilities that are transforming water into potable, drinkable water. Okay, and we'll talk about that in a little bit too. Okay, so surface water is anything that is on the surface. So I have this lecture kind of separated into two modules. First, we'll talk about the water on the surface, and then we'll talk about the water below ground. Okay, so this is all about surface water. So surface water is anything that is precipitated onto the ground and has runoff. Okay, so this can run off in streams, rivers, or it can be stored in lakes, any kind of reservoir that holds surface water. So streams will transport sediment in them as well. We talked a little bit about how water will move sediment with sedimentary rocks, but here we're going to talk about specifically in a stream what that would look like. So some of the sediment grains can roll on the bottom, so we call that along the bottom of the channel. Some of it will move in the suspended loads, so it'll be suspended in the water column and move. And then some are so small that they kind of dissolve with the water molecules and they're basically the size of the water molecules, and they call it that's called the dissolved load or the in solution load. Okay, so those are three ways that sediment can be transported in a stream: in solution, in suspension, or along the bottom of the channel. Okay, so stream velocity is important because the faster the stream is, the more sediment it can move and the quicker it can move it. So stream velocity is dependent on gradient, size and shape of the channel smoothness, and the discharge, which is the water output capacity. So how much water is it actually outputting at the end of the stream? Okay. So gradient is driven by elevation, right? So gradient is slope. So the steeper the slope, the faster the water can move. If the slope is really gentle, like in the Central Valley, the water doesn't move very fast. But if you go up into Kings Canyon or you go into Yosemite, you see that the water moves a lot faster up there because the gradient is much steeper than down in the valley. The size and shape of the channel also helps the velocity of the stream. So the velocity will increase if the channel is narrow. So the narrower the channel, the less it can fan out, and it just moves downstream. So for instance, here we have a wide, shallow channel in time A, or in this A image, and the water here can go out widthwise and then move down. Whereas in this semicircle channel that is not very wide, most of the water doesn't have anywhere to go but down. So the wide channel ends up being a slower river or a slower stream than the smaller channel. So the smaller the area, the faster the water will move. Channel roughness also dictates how easily the water can move, thus how fast it will move. The only problem here is that it's really hard to find a very smooth channel with a high gradient, because in high gradient areas you have a lot of rocks. So if it's a smooth channel, generally it's going to move faster, right? If it's a rough channel with a bunch of boulders, it's holding the water back. The issue here is that most of the time where you see rough channels are in the high gradient areas, and gravity is a much stronger force than the ability of rocks to hold back water. Okay, and then down here in the valley we have very smooth channels, but the gradient is really low. Okay, so the channel doesn't, or the water doesn't necessarily move much faster just because the channel is smooth. All right, and then looking at discharge. Discharge is measured by cubic feet per second. So that's how much water is being output at the mouth of the river. So basically at the terminus, the end of the river. Okay, and these are the world's largest rivers by discharge. The top is the Amazon in Brazil at 7.5 million cubic feet per second of water. That is a lot of water, right? United States makes it on here with the Mississippi at 611,000 cubic feet per second, but nowhere near what the Amazon can produce. When we talk about streams, we talk about two different basic types of streams. So we have braided and we have meandering. Braided is this bottom left picture, meandering is the top left. So braided streams are where there is a lot of sediment present, and they're usually at the terminus of a glacier a lot of times. There's a lot of sediment and there's water being added to that sediment at a rapid rate. And so you see all of these different channels take off in different directions, and they are split by that sediment basically, and they don't find one particular stream path. Meandering streams are a series of bends in the landscape. They have a channel that they are following, and the channel does move and meander through the landscape and evolves, and I'll show you how that works. So, like I said, with braided streams, you can see a glacier here in the background. This is the terminus or the end of the glacier, where the glacial ice is melting and adding to this braided stream, and there's a lot of sediment left from the glacier depositing that sediment, and the glacier is melting, so then it's kind of making its way through in a braided fashion. It's called a braided stream because it looks like you would, braid something. Meandering streams, on the other hand, have a clear channel until they start to change to the landscape, and they kind of just curve around through the landscape depending on what is present. Okay, so here's a diagram of a meandering stream. So as it meanders, on the outside of a curve, it starts to cut into the bank. And where it starts to cut into the bank, we call that a cut bank. Okay, so the outside of every curve is a cut bank. It is cutting into the bank. On the inside, it's depositing things, so it's leaving things behind, and that is known as the point bar. Okay, so the point bar is the depositional feature, and the cut bank is the erosional feature. Okay, so here's another look at that. We have a meandering stream here. We have a cut bank where the bank is being cut into, and all of these kind of orangey areas are the insides of the curve where deposition is occurring, and you see point bars. You'll also see things like oxbow lakes and meander scars in association with a meandering stream, and I'll show you how that forms. So the formation of an oxbow lake is when one of the curves gets too curvy or too sinuous, then they kind of bump into each other, and water takes the straighter path. So after they've kind of bumped into each other, nature takes the straighter path, and then it leaves behind that curve with some water in it, which we call an oxbow lake. After a while, the water starts to evaporate, and there's no constant feeding of this lake, so it becomes a swamp, and then eventually a meander scar in the landscape. So this is what meander scars in a landscape would look like. They would have started as an oxbow lake with water in them, and then eventually they became scars in the landscape. So you can see that this stream has made quite a few turns and twists through this landscape. Looking at drainage patterns at the mouth of a river, there are a few different ones. Dendritic is most popular at the mouth, and then we have radial, trellis, and rectangular, and this depends primarily on rock type and the slope situation. So for radial drainage, you need a center point. So this would be like a center mountain or a volcano. So a volcano will have an iconic peak, and from the tip of the volcano, there will be drainages in a radial fashion outward. Okay, so the radial drainage will come from one center point and kind of move out in a circle, okay, around that mountain. Rectangular drainage will occur in any rectangular blocky type of rock, and it will make kind of like a straight line, turn, straight line, turn, and it looks a little rectangular. And so the drainage pattern is based on the way that the rock will weather. So this happens a lot in like highly jointed rock, where you have these crevices that the water can kind of flow through. And so that's what the drainage pattern you would see. In a highly mountainous area, you would see trellis drainage, which is a center point and a bunch of different drainages that kind of feed it. So you can kind of see in this landscape here, all of these little divots, those are drainage points. And then you have this main drainage here in the center. So they come from these upper peaks here down into this lower area, and then it takes off as the main stream. So they meet this main drainage at a 90-degree angle. So here's another look at what that would look like. So 90-degree angles, and then you have the main stream there. And then dendritic drainage is what you see at most mouths of rivers. And this is where you basically have a center stream, and then it branches out from there. So it kind of looks like a tree branch. It was named from the way that it appears similar to what a dendrite in your brain looks like. So some people say it looks more like a tree, but most people haven't seen what a dendrite in your brain looks like. So it's probably more relatable as a tree. So it's a series of branches from a main network or a main stream. All right, let's talk about surface water infiltration and runoff. So if it's not in a stream and running off in nature as a river or stream or sitting in a lake, it might infiltrate or it might run off. Okay, so water runoff can be, like I said, in rivers and lakes, and then small streams and creeks, storm drainage, and flooding. So those would be more urban water runoff. So we'll kind of focus on that a little bit. Okay, so rural areas are going to look something like this. You have water running off from upstream. So unfortunately here, something happened upstream on the left side of this photo, right? So we have this stream coming down on the right that looks nice and clear, blue waters. And then on the left, we have this orange, just awful looking water. And this is polluted water from something upstream. This could be from construction work. This could be from mining. You don't know. You'd have to go upriver to figure out what it is that's polluting this water that's then polluting this main drainage. Okay? So surface water is really important because if it's great if water runs off and then it goes into our streams, our clean streams and our clean lakes, but when we have pollution that's being carried with the runoff, it becomes a huge issue. So in a deforestation situation, you're going to see a lot more runoff than you will infiltration. Infiltration is key to what you really want to sustain more groundwater, right? Groundwater is easier to store than it is to store in lakes and rivers. You see people all the time trying to build more dams so that there is more water storage on the surface. But if we utilized the infiltration ability of our soil, we could store more water below ground and it wouldn't take up surface space, right? So if we deforest a lot of areas, you're going to see less infiltration and more runoff. Whereas if you have a lot more trees, the infiltration rates are going to increase because the trees soak up the water, which then puts it back down into the ground. Okay, so water infiltration factors are the amount of precipitation, obviously, base flow. So if there's already water on the surface and the soil is completely saturated, then you're not going to see as much infiltration. Soil characteristics, if you have something that does not intake water very well, so like a clay does not absorb water very well. It sits on the surface. You're not going to see as much infiltration. The soil saturation, so that's similar to base flow. If you already have a saturated soil, you're not going to see further infiltration. Land cover, so is it vegetated like this photograph, or do you have concrete over the surface? So if there's concrete, it's not going to infiltrate because the concrete's impermeable. I'll talk about what that term means in a second. The slope of the land, so the greater the slope, the less the infiltration, and the evapotranspiration. All of these things will influence the infiltration, right? So evapotranspiration is like having the plants here. The plants will help to absorb or infiltrate that water. All right, so two factors affect how water will infiltrate into the ground. That is porosity and permeability. You already kind of heard me talk about permeability. So porosity are the pore spaces or the vesicles within a rock or soil. Okay, so these can be pores, they can be fractures, joints, vesicles, cavities, anything with a void space in a rock or soil can fill with water. So the higher the porosity, the more water that can go in. Permeability is the ability of the material to transmit that water from one portion of it to another. So like I said, clay does not allow for high permeability and the water just kind of sits on top. Okay, so let's look at that. So here we have gravel, sand, silt, and clay, and the same amount of water for the same amount of material, it will take 2 minutes to travel through gravel, but 200 years to travel through clay. So gravel has a much higher porosity than clay. So the bigger the particle, the higher the permeability. The smaller the particle, the smaller the permeability. And the permeability is a measurement of the porosity. So if the porosity is low, so there's not a lot of pore spaces, then the permeability is going to be low. So if you have fine sediment like clay, the particle sizes are really small. So you can pack them together, or they can be packed together much tighter. And so the pore spaces, there's not very many. And when there's not very many pore spaces, no water can fit. So that means that the permeability is going to be low. Whereas gravel, it's a bunch of pieces of bigger, gravel-sized rock. They can't be compacted very well together. So they leave a lot of pore spaces. So the porosity is high there, which means that the permeability is going to be high. So water can flow through it really well. Okay, so here's another look at that. Here we have grains that are gravel, let's say they're gravel size with water in the pore spaces. Okay, so pore spaces here. Here we have sediment with cement holding the sediment together, and very little pore spaces. If you have different sizes, so pore sorting, like you see in this image back here, you're going to see less pore spaces. So the better the grains can compact themselves, the less porosity you're going to see. So imagine I filled a jar with marbles and then tried to pour water in it. I could fit quite a bit of water in it, right? Versus if I put marbles in a jar and then I put sand in the jar too. Then I can't fit as much, right? Because sand would be like these smaller particles in here, and the marbles would be these bigger particles. Okay, so if you have two different sizes in the same formation, you're not going to be able to fit as much water in that formation. So some of the factors that control the porosity are rounding, sorting, and cementation. That image kind of already alluded to some of those. So rounding, if they're more rounded, like round marbles versus a bunch of flat marbles, you can fit flat marbles together better because they're angular versus rounded marbles. They kind of round themselves out and they can't fit together like puzzle pieces. So it's the same thing with sediment grains. If the sediment grains are rounded versus angular, the angular ones can fit together like puzzle pieces and it decreases the airspace or the pore spaces. If they're well rounded, it increases the pore spaces. And then sorting is like what I said with the marbles and sand. If it's poorly sorted and has a bunch of different sizes, then you're going to see less pore spaces. If it's well sorted with all the same size, so they're all just round marbles, then you're going to see more pore spaces and more or higher porosity. If it's well cemented, then there's not as many pore spaces versus no cement, there's more pore spaces, right? So these are the factors that control the amount of porosity that you would see in a particular rock or formation. Okay, so one of the cool things in kind of urban runoff development is the establishment of something called permeable pavement. So as you probably are aware or have seen, when it rains in Fresno and it hits things like our concrete or our asphalt, it runs off. And whatever was on that surface runs off with that water. And then it goes into all of our storm drains, goes into our stormwater basins, so all those big basins that have a big pit in them, those are all stormwater basins, and those hold our stormwater when we get too much water, or too much rainfall. And it consists of all of the things that were on the surface. So in order to prevent pollution and to increase infiltration in a particular area, people have started to develop something called permeable pavement. And that is pavement that is permeable and allows for infiltration of water when it rains. And so this is a speed test that I got to participate in, which was really cool, where they set up two ice chests. I started the video a little late, so you can already kind of see it's starting. Two ice chests. One is here on this impermeable concrete, and then there's another one over here that I'll pan to that's on this permeable concrete. And you'll see which one makes it to the drainage faster and kind of what happens. So hopefully this video will play. So here you can see this water has already made it to the drainage, and this guy over here has not gotten past the first 12 inches of where water is coming out as it's infiltrating into this permeable pavement. And here you can already see the drain is backing up, and there's not even that much water coming through here. And all of this stuff is polluting the surface water. Whereas here we just have water going straight down into the ground. So pretty significant. Okay, and then here's another one that I got to see where they did a parking lot. So all of the parking stalls were permeable pavement, and you can kind of see how far, from a water truck's perspective, how far the water will get and how quickly it infiltrates. So you can see the water infiltrates fairly quickly and doesn't even come further than halfway up the parking stall. Whereas if this was regular concrete, it would be running all the way to where I'm standing. But it is not, because it's quickly infiltrating. Okay, so those are just some of the things that we're doing to try to work on surface water runoff, especially in urban areas. Fresno has not caught up. This is in the San Diego area, and I've seen it in San Francisco areas and Sacramento. But hopefully Fresno area will catch up soon, and that'll be really important for continuing our surface water cleanup and making sure that we have clean, fresh, available water for everybody to drink. All right, so that's it for surface water. We'll talk a lot more in detail with groundwater in the next video, and I will see you guys then.